examples that we had given. Remember, we said you flip a coin 3 times, write down the sample space, and we also have another example that we said we are going to revisit it, where we said there is a box that contains 4 slips of papers numbered 1 up to 4, and 2 slips of paper are drawn in succession, and we are required to give the sample space S if we assume that there is no replacement. And I want you to bear in mind that we said sample space is very, very important because it helps us to compute or to calculate probabilities of events. So let us start with the flipping of a coin 3 times. So I want you to understand that to get a sample space, we can use a tree diagram. So what happens is that we have, in the first instance, when we toss a coin, when we flip a coin once, it's either we can get a head or a tail. That is in the first instant. So let me indicate that this is the first trial. Now, in the second, now we are looking at what did we obtain in the first. If we obtain a head, still we are still having a chance of getting a head or a tail in the second. Assuming that in the first flip we obtain a tail, we can still obtain a head and a tail in the second. So now, this is the second trial, the second flip. Now, in the final one, because we are flipping the coin 3 times, it now depends on what we obtained in the first and what we obtained in the second. Assume the first was head and head, so we still have head, so head and tail. Assume it was head first and tail second, we still have a head and tail. Assume it was tail first and head second, we still have head tail. Assume it was tail first and tail second, we still have head tail. So now, when we talk of the sample space, we need to remember the definition. It is the totality of all possible outcomes. Possible means what possibly we are able to obtain from that particular experiment. So when you do it even at home, you flip the coin yourself 3 times. When we talk of the sample space, whatever you obtain must be part of this. So you follow the branches. It means here we talk of head, head, head. In this branch, I'm following the branch from the beginning, head, head, tail. So this is H, H, T. Then the other one is H, T, H. H, T, T. T, H, H. I'm sure we are following because you are just following the branch until where it exits. So we go to tail, head, tail. Tail, head, tail. Tail, tail, head. Tail, tail, head. And then finally it's either you obtain all the tail, tail, tail. So the sample space, as I said, you need to write it as a set. So it means for this particular experiment, the sample space S will be given by either you obtain all the heads, semicolon, HHT, H, TH, H, TT, THH, THT, TTH, and TTT. We write it in the form of a set. So our sample space basically is the set containing this particular event. Also, these are events. Remember, we said events are subset of the sample space. Obtaining all heads, 3 heads, that is a head in the first, a head in the second, and a head in the third, becomes an event. So this is an event, this is an event, this is an event, this is an event. All these are events. And remember from the work that we were doing, now you can actually say the cardinality now of the sample space for this particular experiment will be 1, 2, 3, 4, 5, 6, 7, 8. The cardinality will be equal to 8. Remember the cardinality, we are simply looking at the number of elements of that particular set. And a sample space being a set, then we can also define its cardinality or the number of elements in that particular set. Now let us move on to the second, and I'm sure you are able to extend this experiment to flip, when we flip a coin 4 times, but of course it will be quite a number of elements that will be contained in the sample space S. Now let us move to a box containing 4 slips of paper numbered 1, 2, 3, and 4. 2 slips of paper are drawn in succession. Give the sample space if no replacement. This is very, very important. We need to understand we are talking of no replacement. So what happens, we can still use the probability tree diagram. But what differs now, our tree diagram will not have 2 branches, because the possibility when a box has got 4 slips of paper, every time you pick a paper, there are 4 possible outcomes. So in other words, we need a tree with the 4 branches. So we will have, in a single pick, we will have either you can pick a 1, a slip numbered 1, 2, 3, 4. But remember, we are told that this process is conducted twice. And we are told there is no replacement. So assume that a paper 1, a slip 1 has been picked. So in the second part, we don't expect a branch to have also the paper 1, because paper 1 has been removed already from the box. So we will have 3 branches. That is 2, 3, and 4. Now assume that in the first we picked 2, in the second trial, because there is no replacement, 2 has been removed from the box, so we don't expect to have it. So there are only 3 possibilities. You see, our branch is reduced, it's no longer 4 branches. So we will either have a 1, a 3, a 4, because 2 is no longer part of the box. 3 has been picked, so we can either have a 1, a 2, a 4. And 4 has been picked if we follow this branch. It means we will have a 1, 2, and a 3. So from this, we are able now to write down our sample space. So the sample space is 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4, 4, 1, 4, 2, and finally 4, 3. What does this mean? It means, for example, in the first, you obtain a 1 in the first pick and a 2 in the second. Ladies and gentlemen, I want you to appreciate why we are devoting more time to this idea of sample space. For you to be able now to calculate the probability. For example, if you are asked, what is the probability that you get a 2 in the first pick and a 3 in the second? You can't answer that unless if you are able to completely define your sample space, so that from there you are going to see in our subsequent discussion how then this idea of a sample space will help us. And I want you to take note that each of these are called events. This is an event. This is an event. And so forth and so forth. And you would appreciate that an event is a subset of the sample space. Now let us move on. I'm sure we've covered these 2 examples that we promised that we were going to cover them. Now we want to move on to illustrate more issues regarding the sample space, events, and also operations on sets. Remember, we did operations of sets where we looked at the union, we looked at the intersection, and we also looked at the complement. Now we are going to go to this example that we illustrated. A box contains 6 equal packets. You'll bear with me here. 6 equal packets of accessions for a Bambara, for Bambara groundnuts, which are numbered 1 to 6. 1 packet is randomly selected from the box. I want you to picture what is happening. we have a large box. In this large box, we have small equal packets. The idea of the packets being equal is to show you that to pick a particular packet is equally likely. So there is no bias. So we have packets like this in that box. 1, 2, 3, 4, 5, 6. No, there are 6. Packets are 6. They are numbered 1, 2, 3, 4, 5, up to 6. So this is the scenario that we have. That is our box. Now, we are required to determine the sample space. What is the experiment? One packet is randomly selected from the box and observe what number is on it. So our sample space S, from what we have been doing, will be given by 1, 2, 3, 4, 5, 6. That is the sample space. So it's either you are going to pick a packet which is numbered 1 or 2, 3, 4, 5. And I want you to take note that the number of elements which we write as is actually equal to 6. We've got 6 possible outcomes. So I want us to define some events. Suppose we define an event Suppose we define event E1, which is getting an even number. E1 is the event getting an even numbered packet. Even numbered packet. That's an event. So what is the event E1 in terms of set? Remember, it is a subset of S. So E1 is the set. In other words, we are looking at what are the even numbers in the sample space. So it will be 2, 4, and 6. Now, let's define E2, event E2, as getting a number less than 4. So E2 will have elements, what? 1, 2, up to 3. Now we can also define E3 getting a 3 or a 1 or a 3. So E3 will have elements 1 or a 3. Now we will also define getting an odd number, E4. What are the odd numbers there? You see, we will have 1, 3, up to 5. Let's define getting a negative number. Do we have a negative number in our packets? We don't have. So E5 will be an empty set. Remember how we write an empty set? It will be just a set without elements, or we simply write it as phi. Phi or those two braces, implying that it's totally an empty set, it has no elements. What is E6? Let me define E6 as getting a number that is less than 7. E6 as the event getting a number less than 7. I want you to take note that E6 will be the entire sample space, 2, 3, 4, 5 up to 6. Because whatever packet you are going to pick, if you observe the number on that packet, it will always be a number which is less than 7, because we don't have a number that is greater than 7 in the box. Now, so this is how we define the events. And I want you to further appreciate the fact that an event is a subset of the sample space. That is very, very important. So what is the probability of getting E1? Probability of getting E1. You see, the events are equally likely. And for equally likely events, we calculate the probability as a total for E1 over the total sample space. Let me give you the formula here. It is the number of outcomes in E1 divided by the total number of outcomes in the sample space S. This is only possible for equally likely events. So in other words, it is the number of elements or cardinality of E1 divided by the number of elements in the sample space. How many elements do we have in the samples in E1? There are 3. So it will be equal to 3 divided by the total number 6, which is equal to half. So there is a 50% chance that we are going to pick an even number from this particular experiment. Now, what is the probability of E2? Probability of E2 using the same approach, we are going to say 3 over, it will be equal to 3 over 6, which is equal to still half. What is the probability of E3? What is the probability of E3? E3 will be 2 over 6. Where am I getting 2 over 6? Getting a 1 or a 3. We have 2 elements in that particular event, so we are going to divide it by the sample space, and so that we will have a 1 over 3. Now, what is the probability of E4? E4 is equal to 3 over 6, which is equal to a half. There are interesting things that we are getting here. Now, what is the probability of getting an even number or a number less than 4? Probability of getting an even number or a number less than 4. You see, the idea of operations on set is coming on. So when we talk of or, it simply means the union of 2 events. Even number or a number less than 4. So which events are we trying to unite here? I will clean here to illustrate this part. Probability of getting an even number is E1. So we want the probability of E1 union or a number less than 4, E2. E1 union E2. So how do you find that probability? What is the probability of E1? E1 is 2, 4, 6. What is E2? E2 is 1, 2, 3. So what is E1 union E2? That is very, very important. The aspect of uniting sets. And I want you to go back to our work on basic mathematics and make sure you appreciate what we are talking about when we talk of union. Let me give you the set E1 union E2. E1 union E2 will be equal to 2, but we don't list 2 twice. So let me start with 1 actually. 1, 2, 3, 4, and 6. So 2 is not listed twice. So to get the probability, it will be still number of elements in E1 union E2 divided by the number of elements in the sample space, which is equal to 5 over 6. You can see how many elements we have in the E1 union E2, and also how many elements we have in the total space in the sample space. That one we know. Now, what is E1 intersection E2? E1 intersection E2. That is very, very important. E1, 2, 4, 6, intersection E2. There is only 2. So that is the common element. You see, we are showing now the idea of union, the idea of intersection. So E1 intersection E2 is only 2. In other words, what is the probability of getting an even number, that is E1, and getting a number that is less than 4? And stands for intersection or stands for union. That is in the context of sets, in the context of probability. So getting an even number and a number that is less than 4, it will be equal to 2. It's not 2, it must be 1 because we only have one element. So it will be equal to 1 over 6. Where am I getting 1? E1 intersection E2, probability E1 intersection E2 is equal to the number of elements in the intersection of E1 and E2 divided by the total number of the elements in the sample space. So that will be 1 over, because there is only 2 which is common, it will be 1 over the total sample space. Now let us move on to look at E1 intersection E4. E1 intersection E4, I'm going to clean here a bit for you to see what is happening. E1 intersection E4. Let's go to E1. What is E1? E1 intersection E4. E4 is 1, 3, 5. E1 is 2, 4, 6. Do we have any common element? No. So E1 intersection E4 is actually 5, which is the same as this. It's an empty set. In other words, it is a rare event. What does that mean? And what is the meaning of this? What is E1? E1 means getting an even number. What is E4? E4 means getting an odd number. Do we have an even number which is also an odd number at the same time? We don't have. Remember the meaning of AND. AND means the two events must occur at the same time. When the two events, that is getting an even number and getting an odd number, must occur at the same time. So it's not possible. It's a rare event. So probability of E1 intersection E4 is actually rare. It is a rare event, an impossible event. Remember I said last time when you probability of meeting a donkey that can fly, it's rare, it's not possible. If you see a donkey that is flying, you must know that you have met something which is supernatural, outside the natural world. So that is the same concept. It is not possible for you to get an even number and at the same time an odd number. Now, what is the probability? We said E1 intersection E4 is a rare event. Is a rare event. Now, and we also, what is the probability of getting a number less than 7? In other words, we are looking at probability of E6. A number less than 7. Using the same formula, it will be number of elements in E6 divided by the total number of elements in the universal, which will be 6 over 6, which will give us 1. You see, ladies and gentlemen, we are getting 1 because it is a sure event. In that box, all numbers which are found inside, they are numbered from 1 up to 6. The probability that whatever you have picked from that box will always be a number from 1 to 6 is 1. It becomes a sure event. That is how practical now probability is. Now, I want us to conclude, but before we conclude, I want to add a few concepts which I think will be very, very important. I want you to convince yourself in this case that E1 and E4 are disjoint events. What do we mean? E1, event E1 and E4 are disjoint. I'm introducing some few or mutually exclusive. You see the idea of mutually exclusive, it's even used in courts. If you are suspected that you stole someone's donkey somewhere, and you are able, so the event is you stealing someone's donkey. If you are able to prove that on that particular day in question, you were hospitalized, you were in the intensive care unit, you cannot steal a donkey from an ICU in the hospital. So the two events are mutually exclusive. The judge will use the mutual exclusivity of the two events to declare you innocent, because you cannot be stealing and at the same time in the ICU. So what it means is that once you pick a packet which has got an even number, that event, the mere fact that you have picked an even number, it excludes the chance that an odd number can be seen. So when we talk of mutually exclusive events, these are events which cannot occur at the same time. Mutually exclusive means to exclude the occurrence of the other. The mere fact that the other event has occurred, it means the other one will not occur. In a given year, we cannot have drought and flood. Drought occurring in 2014 excludes flood occurring in 2014. Of course, people will always talk in terms of the concentration and distribution of rainfall and so forth. But basically, when we talk of mutually exclusive, I want you to appreciate the fact that the two events cannot occur at the same time. And draw two sets to illustrate E1 and E4. And you will see that there will be nothing in the intersection between E1 and E4, meaning to say they are mutually exclusive. Now, what do we know if events are mutually exclusive? It means their intersection is 0. E1 intersection E4 is equal to 0. This is very, very important. The intersection of E1 and E, there is nothing in the intersection. Now, what happens if we are to get the probabilities for two events which are mutually exclusive? How do we calculate probability of E1 union E4? This introduces us to what we call the addition law of probability. So the addition law of probability applies to both mutually exclusive and non-mutually exclusive events. So for mutually exclusive like this one, it will just be the sum of the individual probabilities, that is E1, the probability of E1 plus the probability of E4 will give us the probability of E1 union E4. And remember, E1 union E4 means either E1 occurs or E4 occurs or both. But in this case, both will not appear. That is why we are not interested in the intersection. But assuming that E1 and E4 are non-mutually exclusive, for non-mutually exclusive, how do we calculate probability E1 union E4? The probability of E1 union E4 will be equal to probability of E1 plus probability of E4, but we will have to subtract the probability of E1 intersection E4. I think here I need to illustrate so that you see what we are talking about as we conclude. Now, why are we subtracting the intersection? If E1 and E4 is not mutually exclusive, is non-mutually exclusive, it means the events can occur at the same time. So if the events can occur at the same time, it means they have something in common. It means they have something in common, which is E1 and E4. That is, if they are non-mutually exclusive. So if they have something in common, what is E1 union E4? You see, E1 union E4, I will shed the region to show you the region that we want. This is the region that we want. And I'm sure all of you will appreciate why we are studying sets in basic maths. Because it helps you to understand actually the concepts that we are covering. So E1 union E4 is that shaded region which is shown there. But now, when we want to calculate the probability of E1 union E4, if we have that scenario, the moment we put this and we say probability of E1, it means we are going to take this region. This region, that is probability E1, plus probability E2, E4, sorry. When we take probability E4, which region are we taking? I'm going to use a different color. We are going to take this region. I'm going to take this region. What has happened? It means we have double counted the intersection. Do you see this region here? This region has been double counted. When we took E1, we counted it. Now we are recounting it as we are taking E4 because the two events, they are not disjoint. So once we do that, we need to subtract that region once because we don't need to double count. So we'll say minus, what is that region which we have double counted? It is probability of E1 intersection E4. So that means we have to subtract that part. Now, what are exhaustive events? Two events are said to be exhaustive if the sum of their probabilities is the entire sample space. I'm going to illustrate this by a simpler example, but I want you to identify which events, which amongst all those that I've given you, are exhaustive. So, if we flip a coin once, probability of getting a head is half. Probability of getting a tail is half. So, probability of a head or tail is equal to half plus half, which is equal to 1. So, it becomes a sure event. It means the event obtaining a head and a tail is actually exhaustive. So, ladies and gentlemen, we have covered the introductory part to probability, which is very key for inferential statistics. I want you to go through this video together with the notes which are posted on Moodle and underline some aspects which you feel needs further clarity. When we meet, I'm going to introduce the general rules for probability, which is the sort of the axioms, we call them axioms of probability. And I'm also going to revisit the addition rule that I've already introduced here, and we'll move on to look at the independence and dependence of events, that is the conditional probability, before we move on to look at a very important theory called the Bayes theory with the wide application in the biological sciences. Thank you very much and enjoy.